All right, the plan today, first take a few minutes to finish our Excel demos from chapter 2. This is kind of serving as both just a more general introduction to how Excel works and also how to um, create graphs based on data. So we're kind of serving two purposes with this, which is why it's taking a little bit longer. And once again, just in case in case you forgot, if you want something that's a little bit more structured of an introduction to Excel, we're kind of, hitting the necessary points as we come up against them in the course. There's information in the lectures, information in the textbook. Google is a great resource. But if you want something that's kind of mainly structured toward Excel, focused on Excel, just um, a, a more structured learning environment for the Excel material if you're really struggling with it. Take a look at that Coursera course. Again, you can take it for free. Just select the audit the course option. And yeah, I mean, I think that's a good resource. Or I'm sure there are other resources out there. I'm sure there are YouTube, video series, tutorials, things like that. But that's just the one that I have found and that I recommend. So um, that's our plan to start with, and then we're going to move into chapter 3, starting on sections 3.1 and 3.2, and that's where we'll be for the next couple of class periods in chapter 3. And the quote of the day today, by the Greek philosopher Epictetus, conceit of knowledge gets in the way of learning. And I think this is, an interesting thing that we run into today is we're kind of in this information age, right? I remember when I was younger, when I was maybe in high school or college, a lot of the difficulty regarding information or knowledge was acquiring it. Now it almost seems like it's the opposite problem. It's that if I go to Google and I search whatever thing I want, I have some reliable stuff, some conspiracy stuff, some, just completely incorrect stuff, some AI stuff, and how do I curate the information that I have, right? I have at my fingertips access to an enormous amount of information all at once. I need to set up some rules and principles to decide how I curate such information, right? What do I trust the, Google AI thing on? Sometimes it's great, particularly like if you're like this, whatever Microsoft program is doing something annoying, I want to make it stop doing that. Like the AI thing I found is really great for that. It kind of knows what you're talking about, even if you don't use exactly the right words or terms or whatever. And we'll just say, go to this, this options menu, you scroll down to this area, uncheck this box and that'll fix it. And if it seems reasonable, then thanks AI, I appreciate that. But if I'm asking it, what do you think about climate change or something, or what do you think about, some complex and difficult topic, probably not going to trust AI as much, right? Um, a lot of people just say, oh, well, we'll just ask an expert or listen to an expert, or, this person's an expert and that one's not, so I'll take the expert opinion. But that just kind of kicks the can. How do you define expert, right? This comes up in a lot of different areas. Is it somebody with a degree in the field? Well, if that's actually your definition, you know, I, I think you could very easily find people with a degree in the field who are saying things that you would agree are absurd in almost any field in almost any scenario. So that shouldn't just be the criterion. How do we practically define expert? I think a lot of us define expert to be if the person's saying what we like, then we're likely to call them an expert. And if they're saying what we don't like, we're likely to call them a clown. So, right. So this, I think, is the central thing is to be skeptical of your knowledge, to say, okay, I don't know everything. There's going to be information out there that contradicts what I say. I don't want to fall into the trap of underweighting it simply because it's something I don't agree with, and maybe um, having um, having a mentality of curiosity is maybe the better way to get around this, right? Just being curious about what other people think and what other ideas are out there is likely to give you a broader perspective than kind of thinking that you know everything. I certainly don't know everything, and even though maybe sometimes I wish I did. But anyway, that's the idea for today. The challenge today, I think, is curating information in a thoughtful way rather than trying to attain information. Okay, so let me bring up the Excel file. And shift my windows around here a little bit. Let me switch my share and we get into it. So this is the Excel file from last time. It's posted on the Blackboard site, and I also popped it in chat last time. But we're going to start kind of from scratch because I know last time was probably a pretty steep learning curve. So we're going to start from scratch with what we did last time. We'll obviously go quite a bit faster than last time. If you missed last time, this is going to feel way too fast. But since we went through this once last time, this is kind of a refresher before we start working on our next problem. So the first thing we noted was we have our bar chart for last digits of weights. We talked a little bit about what this represented last time. But we see these are integers from 0 to 9. These are 50 data points. They're just arranged in 2 rows because it was a little easier to fit everything on the screen that way for 50 of them. I'm going to select all of my data either by clicking and dragging or by clicking one corner, holding shift and clicking the other corner, probably the easier way to go. And I'm going to rename it. I'm going to name it something like maybe weights. I do that by clicking just above the column A marker and typing in whatever name I want to give it. Hit enter. And now Excel knows that this block of cells, this data, is called weights. If I didn't have a couple different data sets on here, a lot of times I'll just call my data set data or something like that. But because I want to have crashes down here, I want to give this somewhat of a unique name. And then we said, okay, for frequencies, I mean, I could go and I could manually count myself how many zeros, how many ones are here. That's pretty error prone, and that's going to take a while. I could ask Excel to do it for me using the COUNTIF function. We also talked about if we want Excel to actually do a computation, whether it's just a simple arithmetic computation equals 3 plus 5, or whether it's to evaluate a built-in Excel function like COUNTIF, we start with an equal sign. Starting our cell with an equal sign tells Excel, I want you to do some calculation in this cell. And the name of the Excel built-in function is COUNTIF. It's going to count the number of cells that satisfy a certain criterion. Just like any normal mathematical function, this is going to have inputs, and those inputs are going to go inside parentheses. The range is going to be the data that I named weights. We see when we type in weights, it indicates that that's the data set that we're looking at. Those are the cells we're looking at. And then I'm going to put a comma. The second input that I have to give it is a criterion. What am I looking to match? I could maybe hard code in 0, or I could just click this cell. I think depending on exactly which version of Excel you have and what year it is and when it was updated and all that, sometimes this works more smoothly, let's say, than other times. The older versions of Excel, you had to do this kind of thing where you input an empty string and then you refer to the cell using ampersand in the cell. So it's kind of a goofy syntax, but the more recent versions of Excel work a little more smoothly. You just kind of click on the cell, and for the most part, it kind of figures out what you want. So we want to count the number of cells in this group of cells that we named weights. We want to count the number of data points in our data set that have a value that matches this red block, 0. And we see that Excel counted 26 zeros over here, and we counted them last time manually for the zeros, and that was what we got. And the nice thing about this, and not only is it nice that I can just type in this formula and have Excel do the work for me, but I actually pretty much only need to type in the formula once. If I look at my cursor when I'm just going around anywhere on Excel, it's this kind of big white plus. If I go on the edge of a selected cell, I see it turns into this kind of like black cross with arrows. That's not the one that I want. If I go all the way down to the bottom right, I see a black cross with no arrows. So there's a black cross with arrows and a pointer. That actually is for like if I double click, I can move the cell around if I wanted to. Control Z undoes, all of the terrible things that in life. I wish there was a Control Z for life decisions, but if you ever, get something wonky happen in Excel, you move a cell accidentally, just Control Z and it undoes it. So not this cursor, but as we move to the bottom right corner, we'll see it change to just the black plus. I double click and drag, and I note that the weights data set still corresponds to the same data that I was interested in, but this criteria cell, it's a relative index. So my frequency count, my function is always evaluating the criterion that is one cell to the left of the active cell. And I see that at the bottom here, I have already typed in a formula that counts up our frequencies. We know we have 50 data points. We have 2 rows in columns A through Y. So 2 rows of 25 columns, 50 data points. And we indeed have 50 data points that were counted. So we're confident with this. And last time we used this to make a frequency distribution, or sorry, a histogram by hand. So we've got our frequency distribution. We made a histogram by hand. Today, let's take a look at making a histogram not by hand. Let's have Excel just make a histogram for us. To do this, so typically you'd be in the Home tab up here up top, Home, Insert, Draw, etc. Home is where Excel is going to by default open to. If you go over to the Data menu, you might or might not have this. There's this little thing over here that says Data Analysis or Solver under the Analyze submenu. It might be in this little drop-down thing, or you might have to scroll over or something if your window is too small. But you may by default not have this. So I'm going to show you how to get this if it's not showing up on your Excel. And if you switch computers or something, you can always refer back to this, or you can just Google, how to draw a histogram in Excel or something, and most likely this will come up. So I'm going to come over here to File, and I'm going to go down to Options. So again, that's up top here, the menu that says File, and then all the way at the bottom on the left, Options. That brings up this Excel Options menu. And if we look at the left here, we have some different submenus. We're going to look at add-ins down here. So we're going to click on add-ins, and you might have no active application add-ins. I've already added these in, so I have them listed here, but you might not. So if you don't see them listed here, the analysis tool pack, I like to add the solver in as well. It's useful sometimes, but the analysis tool pack's the real one we're going to be using. If you don't see it, go to Manage Excel Add-ins down here, and then just hit Go. That pops up another window. I have no idea why they don't just put these in there. It's only a couple of things, but I guess this harkens back to the day when every other thing you wanted to add into your program, you had to put the CD back in the drive and have the computer pull it off of there. And back when we didn't have just a terabyte of memory on every computer. So anyway, just click your add-ins, the analysis tool pack, make sure that's checked. If you want to check the solver as well, that can be useful sometimes. We're not going to really use it in this course, but I like to add it in. Hit OK. And then when you go back to your data menu, you should see data analysis over here. So that's the tool we're going to be using for histograms. We're also going to use that near the end of the semester for making regressions, making regression lines. We're going to use it in chapter 3 is kind of an optional component. I'll show you how to do it, but we're not going to really rely on it too heavily for our chapter 3 descriptive statistics. But if we click data analysis, histogram, so we see that there's a menu here with a lot of different things we can do. We're going to choose histogram, hit OK. And my input, I'm going to select my data. My bin range is going to be these classes. So that's going to be these cells. Again, click and then hold shift and click the end. That selects all of them. I did not include labels, so I didn't select the word class or some other label that might be associated with the data, so I'm not going to check labels. I want to output in a new worksheet ply. Let's just do that. I could tell it to output in a certain area of this workbook, but we'll just do a new worksheet. And we'll chart the output. We'll plot a histogram chart. Hit OK. And there's our histogram. We see that it has this kind of annoying like more category for anything that doesn't match one of the bins. On one hand, it's a little bit annoying because it messes up our histogram. On the other hand, it's actually kind of nice because this confirms that there were no cells in my data set that couldn't be matched to a bin, that Excel just said, I don't know what to do with this, right? This is kind of like an error checking code almost. And I see that there was 0 that fell into this, like Excel doesn't know what to do with it bin. So that makes me confident that Excel got everything correct. If I click on my graph, so instead of clicking on one of these cells, if I just click on kind of some empty white space in the graph, I notice that I have a purple and a blue box over here indicating what data it's using to plot this histogram. I'm just going to come to the bottom right of this group of data here. Note that my cursor turns into like a diagonal double arrow. I'm going to double click and just move up one. All that does is it just changes the data that I'm using for this histogram, for this chart. Just get rid of that more. I don't really want that in the histogram. It doesn't do anything. It's just kind of confusing over there. So instead of having it in there, cluttering things up, I'll just adjust my data window and I get a nice histogram. I could rename it if I want. Oops, by double clicking up here. I could rename my histogram last digit of weights or something like that. I could get rid of a legend by, say, clicking on it and hitting delete. Maybe this one as well. That's not really doing anything helpful. Right, so I could make a couple improvements like this, and I have a pretty nice looking histogram that Excel just cranked out for me. If I wanted to do this a little more manually, I could select this data, these classes and frequencies, come up here to insert. So file, home, insert. And we see there's a whole bunch of different types of charts here. And I'm going to just look at this top left chart, the column chart, bar chart, histogram, whatever you want to call it. If I click on that, I see that I have a bunch of different types of charts. And I have a couple of different column charts. I have 3D charts, I have bar charts, and so on. And I actually just want to select my frequencies. I can see that as I hover over them, it gives me a preview. So I can click on my 2D column chart. Like I've mentioned before, I tend to shy away from the fancier ones like 3D or anything like that because they just come with more issues than they're worth. They look a little fancier, but this gets the point across more clearly. All right, so I do have one downside, and this is one of those things that I don't know how Excel works all the time. It seems like they change little things from one version to the next. Sometimes some chart types and some versions of Excel will let you get away with selecting both your basically classes, your index, and the frequencies, and it'll kind of know what's what. And sometimes, like we saw when I tried to insert a histogram, at least in this version of Excel for this type of chart, it was getting confused. It was trying to plot 0, 1, 2, 3, 4, which is what we see. The blue bars are frequency 0, 1, 2, 3, 4, 5, as well as the 26, 1, 1, 2, 2, which were the red bars. So it didn't work for this one. So we need to come down here to our x-axis, to our horizontal axis labels. And we want to change those because we see that right now we're kind of claiming that the bin 1 has a whole lot of frequency, but it's really bin 0 that has a whole lot of frequency. The 1 is just indicating that this is the first frequency number that Excel saw. The 2 indicating that the second frequency number it saw is a 1, or the fourth that it saw has a frequency 2. But we want to associate with these classes. How do I do that? When I come up to just some white space on the chart, I don't really want to click specific things because then I get different drop-down menus. But just in kind of some white space up here on the chart, let me right click. And I'm going to come down to select data. And I notice that I have some horizontal or category axis labels listed here. And by default, they're just the counting numbers. See if I can scroll. There we go. By default, they're just the counting numbers. So they don't actually have anything to do with our listed classes here. We would like to change these. So let me edit. And then again, let me just select the numbers that I want. I see that it actually gives me a preview. We now have 0 through 9 on our horizontal axis. That's exactly what we want. Let's hit OK. OK again. And we can double click our title if we want. Edit it. Last digits of weights. And there's my histogram. So I could do this completely manually by hand like we did last time, right? Just using the frequency distribution, just draw it out by hand. We could do it kind of semi-manually. If we wanted a little more control over the different details, or maybe I wanted to use, for whatever reason, a 3D column chart or something, or this gives me a little more control over the details, but at the expense of having to, interact a little more with the nuts and bolts. Or I can use the histogram option in the data analysis tool, and that does a lot of the legwork for me. But again, at the cost of, the chart is what you get. Like, this is what you get. And if you wanted to edit the chart, you could go in and, mess with the nuts and bolts here if you wanted to. But that's 3 different ways to get a histogram. Okay, so now let's take a look at the train crash causes. And here we're going to do a similar thing with our pie chart. Our goal is to make a relative frequency chart and then a pie graph. The first thing I'm going to do if I want a relative frequency chart is I need to get a frequency distribution to start with. I need to count just the number of different types of accidents. Then I can divide each of those numbers by the total to get a relative frequency, to get a percent of the data that are T, E, H, or O. And then I'll actually, because a pie chart is representing relative frequencies as circular segments, I'm actually going to figure out an angle for these as well. So what proportion of 360 degrees gets attributed to track causes or equipment causes? And then I'll draw my pie chart by hand. And then we'll use Excel to draw the pie chart using the Excel functions. Okay, so to count my frequencies, well, first let me give my data set a name. I see again there are 50 of these, 2 rows, 25 columns, so 50 data points. And let me give it a name. So I selected it and I'll call it crash. That'll be the name for this data, train crash causes. Just like above, I'm going to use the COUNTIF built-in Excel function. And because I want to ask Excel to do something, if I just type COUNTIF crash and whatever, what is it, C14, we see it does nothing, right? It doesn't do anything because Excel is just looking at this as a bunch of letters and symbols put in. It just says, it just thinks to itself, okay, you want me to display these pixels in this location. But if I start with equals, I'm telling Excel, hey, I want you to actually compute something. I want you to interpret what I'm going to type in as some kind of arithmetic operation or function or something like that. So I have COUNTIF. If you hit tab on your, if you get partway through, I go down select COUNTIF and hit tab, it'll just enter the rest of it in there for you. What's the range? What's the data set that I'm interested in? The crash data. So I'll start typing it. I see crash came up, so I'll just hit tab and it'll autocomplete. And what's my criterion? I want to count the T's. Let's see if that works, and it does. Again, if you have an older version of Excel, it might be a little less happy with, matching the criterion this easily, but here it works just fine. And then again, I'm going to double click on that bottom right-hand corner and drag down. I'll spot check another one just to make sure that everything seems to be working right, and it does seem to be working right. I get a total frequency of 50. That's in line with the total number of data points that I have, so I'm happy with that. Okay, so I have a frequency distribution here. If I wanted to, I could go ahead and, for instance, insert a histogram, right? And then change my axes to, or my horizontal axis to TEHO. Let me actually even do that really quick here. Just select data, edit our horizontal axis labels. Right. So I could make a histogram for this. That would be fine. But I decided I want a pie chart for this. That's how I want to present the data. I need a relative frequency now. I want to know what proportion
Excuse me, sir.
of,
I have a
yeah,
question. Can you
question.
please again explain me how you got it for E, H, and O after you made it for T?
Yeah, so I type the formula in here, and then when I select this cell that has the formula in it, see, like normally my cursor is this big white plus. If I select the very bottom, or if I hover over the very bottom right of the cell, it turns into this skinny black plus. Not this one, not the one if I'm on the border of the cell somewhere else, where I have the cursor and the arrows, but this one. If I double click here and drag, then it fills the other cells in with the same formula. And again, with that kind of relative referencing for the criterion.
Oh, got it. Thank you so much.
Yeah, definitely. Yeah. Yeah, so we now need a relative frequency. So I want to know what proportion of my data points are T's. There are 23 of them, but what proportion is that? So here I want to, again, do a calculation. So I'll do equals, and I want this cell divided by the total. Right, that's how we find a relative frequency. I look at frequency divided by total. And that gives me 46%. If yours, came up as 0.46 or something, you can just come up here and click the percent button, and that'll change it to a percent. It makes it look a little nicer. Now we might be tempted here to drag down like we did before, but we see we get it divided by 0. We get an error. What happened here? Well, let me double click on this cell and see what Excel is thinking. And I realized that this 46% took as the numerator, the cell that was 1 to the left, and as the denominator, the cell that was 1 to the left and 1, 2, 3, 4 down. Well, here, if I go 1 to the left of the numerator, that's fine. That's what I want. But then 1, 2, 3, 4 down actually references the wrong cell. So there's two workarounds here. The first way is, well, there's only 4 of these. I could just enter the formula 4 times. It's not that big of a deal. The other workaround is I could lock a cell. I could say, okay, when I copy this formula down, I don't want you to refer to the cell that is 1 to the left and 4 down. I want you to always refer to exactly cell D18. The way that I would do this, if I'm on a PC, I hit the F4 button. Don't hit Alt F4. That'll close your program, but just the F4 button. And that puts these dollar signs in front of the letter and the number. That locks the cell. If you're on Mac, I think on Mac it's Command T if I remember right, but I might be wrong about that. You might have to look it up. You might have to Google it for Mac. It's been a while since I've used Excel on my Mac. So, but on Windows, you just hit the F4 button and it puts these dollar signs in front of the cell. Of course, you select the cell you want first. So you select this D18 and then hit F4. That locks the cell. And now when I drag down, I see the D15 that is not locked did come down by relative reference. It's the one cell to the left is the numerator. That's what I want. But the denominator stayed exactly that same total. Again, something a little more advanced. Um, if you don't want to deal with that, you can just enter the formula 4 times. Not a really big deal. But we see these are the relative frequencies. So I want a circle where 46% of the circle is attributed to T, 18% to E, 24% to H, 12% to O. But when we're looking at circles, we're a little more used to how many degrees are in a certain chunk, right? Like, so 90 degrees is like a right triangle, 45 is half of that, 180 degrees would be half the circle. So for the angle, I want to take 360 for the number of degrees multiplied by this asterisk, the star is times 46%. So I want to attribute 46% of the degrees to track failures. So that's a little over 160 degrees being attributed to this first spot, about 86 degrees to human error, and so on. So let me jump over here and we will make a pie chart, pie graph by hand. So I'll start by drawing a circle. Probably won't be a very pretty circle, but there's our circle. Now I'm going to pick just a couple of, I'm not going to do these in a specific order. I'm not going to follow TEHL. I'm going to pick the ones that make it easy for me to draw. So I think I'm going to start with human error because 86 degrees is just about 90 degrees. So I'll start with a vertical line, a vertical radius, and then basically a right angle here. And if I want to, I suppose I could, shade this in black and, make a note over here that black is human error, or I could just put an H in that spot. Okay, what else would be easy? What else is an easy number of degrees? Well, O is actually pretty easy. 43 degrees, pretty close to 45. That's about half of a 90-degree angle. So my next 90 degrees would be like here. I want about half of that. So this 45 degrees would be for other causes, O. My other two I have are 64, let's call it 65 degrees. That's not a super nice one. I mean, it's a little more than 2/3 of a 90-degree angle, or 165. Neither of these are super nice. 165 is a little less than 180. It's about 15 degrees less than 180. So maybe I'll go with that one, right? Going to my left from this vertical radius, 180 would be like here. I want to go 15 degrees less than that, so just a smidge less than that. Maybe something like that. And that'll be track issues. And then E for equipment is what is left over. And that does look a bit less than 90 degrees. 64 to 65 degrees is a bit less than 90 degrees. This seems pretty reasonable. So that's how I would make one of these by hand. You can see that making a pie graph by hand is not super easy, even with just 4 slices. If we had 8 or 10 slices, it will be much more challenging. So, I mean, I suppose if we had like a compass and a protractor and all that, it would be a bit easier. But we can also just ask Excel to do the work for us. Let me select my classes and frequencies, go up to insert, and instead of trying to do a histogram, see here, Excel figures out that because T, E, H, and O are not numbers, it knows that those are probably labels, and it figures it out a little better than the previous bins, which were numerical. But instead of doing a histogram, I'm going to come up here and choose a pie chart. And again, there's a couple different kinds. There's all kinds of different ones you can use, but I just like the top left. And we see it gives us a pie chart. It doesn't look exactly the same as ours because we kind of, we didn't follow any particular order in ours. We just chose the order that was easier for us to kind of work out where the different angles are. But it's the same representation, right? The track issues, which are colored blue over here, looks like that's about the same size of slice as our track issues in our hand-drawn one. Same with our about 90 degrees from human error and this like kind of ugly green color, our human error one over here, about 90 degrees, right? So it looks like it's representing the same data, even though the chart looks a bit different. And we could rename our chart. So something like train crash causes, and there we go. If I wanted to be a little more descriptive in my class, I could, name it track or something like that. That kind of messed it up. I don't know exactly why, but because now the T's don't match, but can I undo? There we go. But I could, be a little more descriptive in my labels if I wanted to. One of the downsides of a pie graph is this shows proportions really well, but it doesn't show me absolute number very well. Right? Is this representing 10 crashes, 50 crashes, 500 crashes? It's not clear from the pie chart. There are other things you can do in the chart design or the format area where you can look at different options where sometimes you can list either the percentages on top of the pie slices, which I think is a bit silly because the whole point of the pie slices is that they're visually representing the percentages. But there is a way, and I'm not seeing it at just this second, but there is a way to represent the number. So instead of percents being on here, it'll say 23, 9, 12, 6. So that in almost all of these charts, I mean, there's a practically infinite number of things you can do to play with it. There's just so many different options in the chart design and format. But when you use these things, I would say, uh, always ask yourself, is what I'm about to do, Is it making it easier for my audience to digest this? Is it making something clearer or more informative or less confusing? If not, then probably don't do that. And even worse, if it's making it worse, if it's making it more confusing or more difficult to interpret, definitely don't do it. If you like the aesthetic better, or if you think it's just a nicer graphic design and it doesn't make it any worse, well then, it's not a big deal. But we definitely don't want to do things that make the situation worse. And for instance, switching our chart to a 3D chart. That didn't work how I wanted it to. But will you let me switch to a 3D? There we go. Switching it to a 3D chart brings in this issue of parallax, right? That Excel is dividing the pie up with these same relative proportions, but the problem is now the purple in the back is further away from us. It looks smaller, and the red is close to us and it looks bigger. We've taken a chart whose entire goal is to represent areas visually proportionate to their relative frequencies, and then we've changed the visual representation of the areas. So I don't understand 3D pie charts at all. It does exactly the opposite of what it's supposed to be doing. You put in all this work and then you make it 3D, and that distorts the actual areas and makes the relative frequencies. It muddies the waters anyway. Okay, so those are kind of the main two graphs, histograms and pie charts. But as you saw in the charts here, you could make line charts, you could make scatter plots. There's all kinds of things, all kinds of different charts and things you can make up here using Excel. Okay, I think I would like to bring up just two examples. We're not going to go through the details of these. We're just going to look at the completed example. So here's an example of CPI, the Consumer Price Index, or essentially the inflation rate change. So change in the CPI from year to year, going from 1913 to 1920 or to 2021. So a span of about 100 years or so. Note that Consumer Price Index, it's a basket of goods, and we say, what would it cost to buy this basket of goods in 1913 versus 1914 for the same basket of goods? Well, that's dollar denominated. But since we're looking at the change year over year, we're kind of staying within that same unit. Comparing 1914 dollars to 1913 dollars, they're staying kind of in that same unit. And in fact, we're really looking at here the difference in that unit of dollar from one year to the next. That's really the goal of looking at inflation, or the CPI numbers. And here we have a graph here. This is a bar chart, but it's not a normal bar chart. It's kind of like a time series graph, right? My horizontal variable is time, as the date. See 1913 here and going on from there. And the height of each bar is actually the data point. So this is not like a histogram like we just saw, where the height represents frequencies and the horizontal axis labels represent bins. Here, really, the horizontal axis represents time and the height represents value. Why did I choose a bar chart here, or a column chart, instead of choosing a line graph? Well, because inflation year to year is going to jump around a lot. If I knew there was high inflation last year, that doesn't tell me much about what the inflation is going to do this year. If I was graphing the price level of the basket of goods, if I was graphing this data over here, that in 1913, this basket of goods cost $9.8, in 1914, it cost $10.0, and so on, here I would use a line graph, because I think that if I knew that it cost $19 last year, it's probably going to cost more or less that amount this year. But since I'm looking at changes, I'm going to use this column chart. And I can see at a really quick glance, there were a couple of periods of high inflation, notably like the 70s. Your parents or grandparents might remember the 70s and this hyperinflationary period when mortgage rates were like 12 or 15%, much worse than what we're seeing in the last couple of years. There was a period around the end of World War II. Period looks like just before World War I. And then there were even a couple of deflationary periods, periods where the dollar was worth more, where you could buy more for $1 the next year than you could the year before. So not something that we've seen in the last, nearly 100 years or so, but quite a while back we had a bit of deflation. And then the other thing I wanted to look at is this S&P 500 data. This goes from about 1926 to 2022. And again, if we just plot the data like this using a line graph, the line graph is sensible because if I know what the S&P index is, this year, it's probably going to be about that same value next year, maybe plus 10%, maybe minus 5%, but it's going to be more or less in the same ballpark. If I plot this, I see my 2001 housing market, or sorry, .com bubble and crash. I see my 07 to 09-ish housing market bubble and crash. I look at these and I say to myself, wait, well, these seem much worse, much more extreme than say even the Great Depression. I mean, look at the Great Depression back here. You can barely even see the little blip in the 1930s. Do we have it much worse off than them? Well, keep in mind that this S&P is roughly speaking dollar denominated, and a dollar meant a very different thing 100 years ago. We're really not comparing the same units here. What I really should look at is the rate of change, say from one year to the next, of the S&P 500. What was the return? Your return on investment for, say, investing in a broad spectrum of stocks in the US stock market, and then holding that investment for a year. Now, all of a sudden, we see, well, the .com bubble and crash here around 01 or so, we see a couple years of, in a row of about 20% declines. We see our housing market crash, about a 40% decline over that year. Looking back in the 70s, we have like the savings and loan crisis, maybe a couple years of 20% decline or so. So about as bad as the .com bubble or about as bad as the housing market crash. But looking back to the Great Depression, we see one year with about a 50% decline, but it's surrounded by 3 more years of what, about 10% decline, 25% decline, another 10. So we got hit with 10% loss, 25% loss, 50% loss, 10% loss, had a good year, 10% loss again, right? Now we can all of a sudden see, okay, yeah, the Great Depression, this big bunch of negative rates of return over here clustered together. Yeah, that actually was a lot worse than the housing market crash or the .com crash. Why can we see that so clearly here? Well, because rate of return from one year to the next is comparing basically, 1 year's dollar to the next year's dollar, and then dividing out that unit, getting rid of the unit to make a percent change. Now, you could say, okay, 1 year's dollar to the next isn't quite the same unit, but it's not that far off, right? We don't have that much inflation or deflation. It's not Venezuela or, Germany or something like that. So we don't have crazy inflation. So from one year to the next year isn't going to be that big of a change in the unit, and we can basically treat it like the same unit. But this number is comparing 2022 dollars to 2021 dollars. This number is comparing 1936 dollars to 1935 dollars. So each of these numbers is kind of scaling out the dollar unit, making a unitless quantity. We like unitless quantities because it doesn't come with these issues of scaling and of inconsistent units and so on. This is a much more, this is a graph that's much easier to interpret as far as, looking at how the economy was doing or how bad certain crashes were at certain points in history. Any questions on any of this stuff, either on Excel or graphing or chapter 2 in general? Any questions on any of this? Okay, give me a second here to switch my share around and swap all my windows around. Okay, so that wraps up chapter 2. That also wraps up our Excel introduction. So again, I know that, some of the stuff in Excel can feel like a steep learning curve, but especially if you were working along with it, if you were working along with me in the Excel files, or if you didn't have it up, you could always come back, watch the recording and go through. If you're watching the recording, you can pause it and try a couple of different things or see, ask yourself, oh, I wonder if this would work, or I wonder how I would do that. What if I wanted a pie chart for the last digits of weights or a bar chart for histogram for the train crash causes? Can I make those work, right? So you can play around with it a little bit. Of course, you can always stop in office hours or revisit the lecture, look at the resources in the textbook. And then, as I mentioned, if you want something a little more structured, there's that Coursera course that you can audit as well for free. Okay, so with that completed, we will move into chapter 3 now. Remember, chapter 1 was an overview. Chapters 2 and 3 are looking at descriptive statistics. We have a data set. We're trying to crunch it down to something that's more digestible. In chapter 2, that was something like a picture, a pie chart, a histogram. In chapter 3, we're trying to crunch our data set down to a number, a numerical descriptor, a number that I can convey to you and say, maybe the average value of this data set is something, and that tells you something about some characteristic of the data set with a single number, not with the 100 or 1,000 or 10,000 numbers that are in the data set. Now, something about measures of center is we have a lot of different ones. We have some that are pretty commonly used, mean and median, some that are a bit less commonly used, mid-range and mode, some that are used in very specific circumstances like geometric mean, harmonic mean. We might punt those to a short supplemental video. There's also root mean squared is used a lot in science. It has a lot to do with things like power and so on. So there's lots of measures of center. Sometimes the context dictates that maybe this measure of center is much better to use than this other one. And sometimes it doesn't. So let's look at a few data sets that we're going to use throughout this chapter. We're going to use these 3 data sets. We have a salaries data set. It consists of 7 data points. These are salaries represented in thousands of dollars. And we're considering this a sample. If I just gave you this data set and said, here are these numbers, these are salaries, you wouldn't know whether it's a sample or a population, but I'm telling you here, this is a sample. So this might be, we're interested in knowing something about the salaries of a company of 500 people, and we have a sample of size 7. The other 2 data sets we're going to use are these tax returns data. So these are returns per day completed by a couple of folks in an accounting firm. We're considering this population data. In other words, the scope of my question is only tax returns completed this week, and these are their 5 days this week that they completed tax returns. So we're considering these data to be population data. Okay, so just a little short detail on notation for chapter 3. We have a data set, and we typically say that our data points are x1, x2, and so on through xn. So n is the size of our data set, or Typically, we just call it the sample size, although if it's a population, it's really the size of the population. So in other words, for the Ashley data, maybe x1 is 5, x2 is 8, and so on. And n equals 5 for the Ashley data because there are 5 data points. Now, typically, to make our lives a little bit easier, typically what we will do is we'll impose an ordering. So typically when I have my data set, the first thing that I'm going to do is put it in order. Now, of course, that presumes that the data that I'm looking at, the values, have a natural ordering and ranking. And in both of these cases, they do. Right? Uh, these are both types of data that have a natural ordering and ranking to them, so we can put them in order. Now, it's entirely possible that we have like the train crash causes or something that has no natural ordering or ranking, or maybe colors of shirts or something like that, no natural ordering or ranking, in which case we can't really do this. But also in which case, most of these measures of center can't be computed for that kind of data. It turns out the mode can be, and that'll be one of its uses, one of its kind of niche cases. But uh, so for most of chapter 3, we're thinking of data sets whose data values are numerical, who have a natural ordering and ranking, who have enough structure to do arithmetic operations on them. Because most of the computations of these measures of center, or in section 3.2, measures of variation, most of them are arithmetic operations. So we need a bit of structure to our data to really be able to compute most of these. So from this point forward, we'll kind of assume that the first thing we're going to do is put our data in increasing order so that x1 is our minimum and xn is our max. We could have different data points with the same value, that's fine. And by the way, when I talk about a data point, I'm talking about a specific association of individual to value. But when I'm talking about a data value, I'm talking about, say the 28. So there are 3 data points that have the value 28. This person and that person and that person all make $28,000 a year. They all have the same data value, but those represent 3 distinct data points. So if I was computing an average, I would represent the 28 3 times. That value occurs 3 times in 3 separate data points. So I will try to be careful about being precise about using the word data point versus the phrase data point versus the phrase data value consistently. So the data point is like the individual that we're measuring along with the value we measure, and the data value is like just the value that we measure. So different data points can share the same data value. Okay, so let's look at the mean. Let me actually zoom this in a little bit so the text is a little bigger. There we go. The mean, or the average, or the arithmetic mean. Um, Stats authors, for some strange reason, make a big deal about not calling the mean the average. And their argument is, well, there's lots of different types of averages, but like we saw up here, there's lots of different types of means too. So just saying the mean is, equally ambiguous with saying just the average. I don't see a big difference between the two. Everybody knows what we're talking about. So mean or average, or if we wanted to be really specific, it's the arithmetic mean is really what it's called. So how do we compute the mean? We compute the mean by adding up the values of all of our data points and then dividing by the number of data points we have. So we just add everything up, divide by the sample size, that's our mean. This is the same old average that you've computed, many times in the past and that you've seen many times in the past. We have some notation to denote the mean. If I have the sample mean, let's say that I'm using x's to denote my data values, or my data points, x1, x2, x3, etc. Then I take that variable x and I put a bar over it. I would verbalize this as x bar. So I'd say x bar equals the sum of the xi's over n. Note that the textbook and some resources will write this as like sum xi over n, or they might even go as far as to write I equals 1 to n, something like that. Personally, I think this so-called sigma notation, it's super nice in some scenarios, like if you're taking calculus, like you pretty much can't get by without using it. But if you don't need to use it, I would not use it. I'd much rather write this out. The reason is that, I mean, I guess here it's, not super complicated, but when you start getting into things like computing the variance or standard deviation, it can be a little confusing if you're not used to the notation to know what's being added up. Here it's kind of obvious, but I kind of try to shy away from the sigma notation. So I'll put this in as a parenthetical note, but the way that I'll typically write these formulas is by just explicitly writing out the sum. So that's our sample mean, x bar. It's denoted x bar. If we're dealing with a population, we use a different notation. Now, it turns out a population mean is computed the same way. We still just add up all the values of the data points and divide by n. So if we're computing it the same way, why do we call it something different? Well, one of the things that we'll be very interested later on in the course, chapter 7 and 8 particularly, is, well, if I take a sample and get a sample mean, that's what the information I have access to. But really, I want to know the population mean. How close is the sample mean to the population mean? If I want to start asking questions like this, I really need two different notations so I can talk about the two in relation to one another. So that's why we're developing this notation now. When we get to chapter 7 and 8, it's going to become extremely important to use this notation correctly. So we're starting it now so that we get used to the notation. The population mean gets the notation mu. This is mu, probably more properly mu, but if I say mu, then everybody laughs, and we're not in Greece, so we'll call it mu. So it's something like mu, and it's the Greek lowercase letter m. So this mu, if we had one of these kind of lines, it would look like this. So it looks like a U with a longer left-hand tail. So mu, we typically represent population parameters as Greek letters and sample statistics as Roman or American or English, whatever you want to call it, letters. So the population mean mu is computed the same way. But in the context that for mu, we would be thinking of the x1 through xn as a population, like for instance, the Ashley or Brandon data, where for x bar, we'd be thinking of the data set as a sample. So if our data represented a sample and we were presenting the mean, we would call it x bar. If our data represented a population, we were presenting the mean, we would call it mu. So let's take a look at we'll start with the tax return data. Take a look at our two population data sets and compute the mean for each of them. So let's start by computing the mean for Ashley. I'm going to call this mu subscript A. If I have different data sets floating around, I might use a different subscript to differentiate between them. Or if I had different data sets for samples, I might, call my other one Y. Oops. I might call my other sample Y and denote those sample data Y1 through YM, let's say, where M would be the number of data points I have in my second sample. So if I have different samples or different populations floating around, that's how I would denote the different statistics or parameters. Now, I think probably the first thing I want to do just for good form, it doesn't really hurt in the mean because addition is commutative, but later on this will help. The first thing I'm going to do is I'm going to rewrite my Ashley data in increasing order. So I have 5, 7, 8, 9, 11. Oops, ran into my median down there. And I'll do the same with the Brandon data just to get it in order for later on. 3, 5, 7, 11, 14. So Ashley's mean is 5 plus 7 plus 8 plus 9 plus 11 over the number of data points that I have, which is 5. I note that 5 and 7 is 12, plus 8 is 20, 9 and 11 is also 20. This gives me 40 over 5, or 8 for Ashley's mean. Now, as much with me being a math guy, as much as I hate units, I do have to point out that these data kind of implicitly have units, right? This is like 5 returns per day or 9 returns per day. So these data implicitly have units. I should check what my units are over here. Well, I have 5 returns per day, added the 7 returns per day, and so on. If I add the same units to one another, like if I add 5 inches plus 10 inches plus 3 inches, they just add together and maintain the same unit. I can't really add different units together. That just doesn't really make sense. And then I'm dividing by a counting number. A counting number like 5, just saying how many data points are there? There are 5 of them. The counting number is unitless. So this 5 in the denominator doesn't change the unit at all. The numerator just stays in returns per day. So Ashley's mean is 8 returns per day. What's the goal of a measure of center? I meant to mention this before and skipped over it, but what is the goal of a measure of center? We're trying to answer a question that's something like what does the typical data point look like? What's a typical data point in this data set? Right? What does a typical day for Ashley look like? She completes 8 returns per day on average. Some days she does a little better. Maybe she gets some easier returns that day, or maybe she, just had more coffee that day or something and gets maybe 9 or 11. Some days a little slower, maybe more difficult returns on those days. Some days she gets, maybe a 5 or something like that. But kind of on average, a typical day for her might look like about 8 returns per day. Oh, So what about Brandon then? Well, we do the same thing for Brandon. 3, 5, 7, 11, 14. We add those up. Divide by the number of data points, which is 5, just like Ashley. And uh, so what do I have here? I have 14 and 11 is 25. And 7, 5, and 3 adds to 15. So this is, again, 40 returns per day divided by 5. So Brandon's mean is also 8 returns per day. He kind of, on average, does as many returns per day as Ashley does. We kind of see just looking at the data. Here we can just look directly at the data set because there's only 5 data points. We're using small data sets to make this manageable, of course. Um, we can look at the data set and we can just see that Brandon, his his performance is more variable. When Brandon has a bad day, it's a really bad day, 3 returns on one of the days. But when he has a good day, it's really spectacular. Where Ashley is a little more consistent. Regardless, though, Ashley has her slightly good days and slightly bad days. Brandon has his really good days and really bad days. But kind of at the end of the week, they've both completed 40 returns total. So they average 8 returns per day. Their measure of center, their typical day, it's kind of the middle of their performance for both of them is 8, at least under this measure, the mean. So that's kind of what this is looking at, right? The mean kind of says, what is the number, say, of returns that if you took your highs and lows, your peaks and valleys, and smoothed them out, and your performance was exactly the same every day, what would that performance be so that you complete the same number of returns at the end of the week as you did when your performance was variable? So if Brandon or Ashley had completed exactly 8 returns every single day, 8 on Monday, 8 on Tuesday, etc., they would have at the end of the week completed the exact same number of returns as they did with their variable performance. Okay, so what about the salary data? So let's take a look at the salary data. Again, we're told this is a sample, so we know it's a sample. And let's put these in order. So it looks like, oh, I missed one. 25 is our smallest. And then the 28s, we have 3 28s, a 30, a 55, and a 100. Again, not really strictly necessary if we're just adding these up because addition's commutative, but this is really helpful for some of our future work. So our salary mean, we're going to call X bar. If we really want to do, maybe we can call it X bar subscript S or something like that, but I think it's clear here that we're talking about this data set. This is going to be 25 plus 28. Note that we have 3 instances of 28. We include that 3 times. We don't like write it down once and skip over the others or anything like that. 30, 55, and 100 over. So I have 3, 6, 7 data points. Let's bring up the calculator. Okay. Switch my share here. Bring up the calculator to help us complete this. So I'm using a TI-83 for our demos in class, but you're free to use whatever handheld or graphing calculator you want. On exams, you can't use a phone as a calculator or like an online emulator, but you can use any calculator that is only a calculator. Now, what we might do here is something like this. and then divide by 7. If I do this, I get a mean of 208. Does that seem like that's a typical data pointer, like that's kind of in the middle or in the center of the data? Well, no, of course not. Number one, we always want to engage our brains when we're doing these things. We don't want to just crank out a formula, forget about what it means, and does 8 seem like a reasonable mean, a reasonable measure of center for the actually Brandon data? Yeah, it does. Right? It's kind of in the middle of their numbers. I also don't want to forget about my order of operations. So what I've done here, I've told the calculator do division first, that's its order of operations, take 100 over 7 and get 14, 14-ish, and then add all these numbers, and then at the end add 14. Well, that's not what I want. Two ways around this. I could either add parentheses before the 25 and after the 100, do everything in one line, or my preferred method is I just got rid of the divided by. I'm just going to compute the numerator by itself and then put the denominator in second. That way I just don't have as many parentheses floating around. I find this to be less error prone. And I get 42. Of course, the answer to all life's questions. If you've ever seen The Hitchhiker's Guide to the Galaxy, or if you've read it. Now, just like above, there's a unit here. This 30, for instance, carries the unit of $1,000, as does each of these other data points. Each of these things we're adding together in the numerator carries the unit of $1,000. The denominator is just a counting number. My mean also carries the unit of $1,000. So the mean salary for the sample mean salary is $42,000, or just 42 in the units of thousands of dollars. And again, we ask ourselves, like, okay, is that sensible? Is that a sensible answer? Yeah, I think it is, right? It kind of falls in between these two. It's kind of roughly in the middle of the data. Or another way of looking at it is if we took these 7 people, just had them throw all of their money from their salary into a pool, and then we divided it equally between them, everybody would get $42,000 if we divided it equally. Questions on the mean? Okay. I'm going to switch my share back because I don't think we'll need the calculator for the next bit here. Okay, so the median, what is the median? The median is, roughly speaking, the middle number or the middle data value. So let's take a look at our Ashley and Brandon data. And here I know I have 5, 7, 8, 9, 11. So let me just go ahead and type that in the right way so that's in order. And for Brandon, I have 3, 5, 7, 11, 14. All right. Oh, a little too far there. Okay, so I've just realigned my Ashley and Brandon data so that each time I copy it now it's in order. We took the time before to place everything in order. Now it's in order. Now, very importantly, I'll put like a double exclamation point here. It's the middle number after things are placed in order when ordered by data value. So 2 things. Number one, of course, our data has to have enough structure that it has a reasonable ordering. There's a natural ordering or ranking, so I can put it in order. And number two, I better actually put it in order first. If I pick the middle number up here, well, these are just kind of arranged in whatever way. Picking the middle number doesn't really have anything to do with the underlying thing I'm measuring. Right? If I just picked, 5 people from the population and told them, here, stand against the wall, and then picked the middle person and made their height the representative typical height for the population, that would be not a very sensible thing to do. But if I told them stand against the wall and increasing height and pick the middle one, maybe the middle height when they stand in increasing order of height is maybe a typical height in the population. So now that I've ordered them, put a check mark next to that, let's compute their median. So what's the median for Ashley? Notation for the median, it's not as important in some senses as the mean. It's usually just MD. Occasionally in mathematical statistics or in some reference books, you'll see the Greek letter eta. Looks a little bit like an N with a long leg on it. So occasionally you'll see the Greek letter eta representing the median, but that's not very common in the intro level books or resources. So we'll just refer to median as MD. So what's the median for Ashley? It's the data value that's the middle value. So it's the 8 here. If I had a bigger list, how would I find the middle? Well, basically what I would do is I would cross off one smallest with one largest, the next smallest with the next largest, and I keep doing that until I get down to one left over. Here I have an 8 left over. And the median just plucks out the data value, so it just carries the unit with it, returns per day. Hey, Ashley's median is 8 returns per day, and her mean is 8 returns per day. That seems good. That seems nice and consistent. What about the median for Brandon? I want to pick out the middle one. Again, if I have a longer list and need to work down to it, I could cross out one smallest and one largest, the next smallest and the next largest, keep going until there's only one left. The median for Brandon is 7 returns per day. And note, we get a little bit of a discrepancy here, right? When I asked for a measure of center for Brandon, I could report the mean of 8 returns per day as kind of the typical performance for Brandon. So that if I watched Brandon for 5 days, if hypothetically, if he had done exactly 8 returns per day every day, he would have got the same number of returns done at the end of the week as he did in his variable state here. Or I could look at it as list his days in increasing order of performance and pick the middle day's performance. This isn't a super well posed problem. What's a typical data point? So we don't have just one answer. We have different ways to approach the question. So maybe in some contexts, giving a mean is the most reasonable, appropriate answer. Sometimes maybe the median is, sometimes something different might be the more reasonable answer. So our measures of center aren't all going to be the same for all data sets. In some cases, like the Ashley data, it happened to be the case that some of our measures of center are going to be the same, but that's definitely not a guarantee. Let's look at our salary data. Oh, there it is. I don't know if I've said this before, but usually I have to complain about Microsoft. So, but OneNote, they've gotten so much better at copying and pasting stuff. It works so well now. Like when I started using it for Zoom classes, it was like every time I copied something and pasted it, it was like crossing my fingers that it wasn't going to just mess everything up. But it works so well now. So got to give kudos where it's due when Microsoft does something good. All right, so what do we have? 25, 328s, 30, 55, and 100. All right. So that is our data set that is now ordered. Super important to do for the median. If you don't order it first for the median and you just pluck out the middle one like this, you're going to basically just get a random selection of something from the data set. It's not going to be at all uh, a good measure of center. But we did order it in increasing order of salary here. And again, we go down and we say cross out one smallest with one largest, the next smallest, the next largest, next, the next, and we're down to one left over. So our median for salary is 28. And again, we just pull the unit right with that, $28,000. Our mean salary was $42,000. Our median salary is $28,000. These are actually quite a bit different, right? Going from 8 to 7 is maybe a 15-ish% change. Going from 42 to 28 is like a 50% change. Or let's say 28 to 42 is like a 50% change, 50% increase, or 42 down to 28 is a 30-some% decrease. A pretty substantial change in this case, right? We might say that, well, there's no difference in Ashley's measures. We might say the difference in Brendan's is kind of negligible, not a big deal. But if I wanted to present, if I was the union rep looking to present an average salary in some sense, or if I was the management, person arguing against the union looking to present an average salary, they might have incentives to pick two very different measures that, that really support their different points that they're trying to make. Um, so which one is right in what context? We're going to talk about that maybe a little bit more in a couple minutes here. Any questions so far? Now let's look at let's look at another example. Let's suppose we have salary data, but let me get rid of one of these 28s. Let me delete the row. There we go. So these are new salary data. So this is different than the previous one. I just got rid of one of the 28s. So what if we had this sample of 6 folks, a 25, two 28s, a 30, a 55, and a 100? And I want to compute a median. It's in order already. What's the median for the new salary data? Well, I cross out a largest with the smallest, the next largest with the next smallest. Well, if I cross out the next ones, I don't have anything left. So I kind of have like this tug of war between 28 and 30. If I have an even number of data points, there's not a clear middle one. If I have an odd number, there's always a clear middle one. But if I have an even number of data points, the middle is kind of like shared between two data points. And particularly if they have a different value, what do I do? Well, in this case, I average my two middle data points. I take 28 plus 30 over 2 to give me 29. I just take the average of those two middle data points. 28 plus 30 over 2 gives me 29. And as always, that is in the original units of thousands of dollars. Right. So if I have an even number of data points, I work my way to the two middle data points, and then I average their values. If I have an odd number of data points, I just work my way down until I get to the one middle data point, and that's the clear, winner, so to speak. That's the median. Questions so far? Okay, and then another another measure of center is the mid-range. This is a less commonly used one, but it has an important use that we're going to see pop up in a couple minutes here. So the mid-range typically just denoted MR. It is the average of the extremes. So where the median kind of forgets about all of the extremes and just looks at the middle of the data set, the mid-range kind of forgets about the whole middle and just looks at the two extremes, the max and the min. The mid-range is x min plus x max over 2, or if we've ordered everything, it's x1 plus xn over 2. It's the average of the extremes for the mid-range. So what's the mid-range for Ashley? Her worst day was 5. Her lowest number in the Ashley data set is 5. The highest is 11. So if I average 5 and 11, I get 8. And the 5 and 11 both carry the original units, so this is 8 returns per day for Ashley's mid-range. Hey, her mid-range matches her mean and her median. What about for Brandon? Brandon's worst day was 3 returns, but his best was 14. That's 17 over 2, or 8.5 returns per day. And what's the mid-range for the salary data? Well, that's 25 to 100. So 25 plus 100 over 2. Well, that's 125 over 2. That's like 120 over 2, which is 60. And plus 5 over 2, which is 2.5. Our salary data mid-range is $62.5 thousand. One thing that I wanted to mention earlier and I skipped over, just kind of to point this out, Ashley's mean or average is 8. It happens to be a member of her data set. Most of the time with our measures of center, most of the time the quote typical data point or the measure of center we report, most of the time is not going to be a member of the data set. Note that Brandon also had a mean of 8, but there was never any day that he performed at exactly that level. All that 8 represents is at the end of the week, at the end of these 5 days, he got a total of 40 returns done. If he had performed perfectly consistently, how many per day would that have been? That would have been 8 per day. But that's not to say that he ever performed exactly at 8 returns on any particular day. Now the median, of course, because we're plucking numbers out often, often the median is going to be a member of the data set. It certainly will be if we have an odd number of data points. But in the mid-range, again, we notice that Ashley's mid-range was 8 returns per day. That happens to be a member of her data set, but the mid-range for Brandon ends up being even a number that, that maybe doesn't make sense. Like, how do you do a half of a return in a day? 8.5 returns per day. But it's still, that's his mid-range. So the measure of center is likely not going to be a member of the data set. It might even be, and probably will even be for most of the measures of center most of the time, in a format that is maybe even inconsistent with the format of the data in the data set, right? Like if we're measuring a discrete variable like number of full returns completed per day, we're not getting a discrete number out as, say the mid-range or, necessarily as the average or anything like that. Okay, so something that I'm going to leave as kind of an exercise over the weekend, and we'll talk briefly about this next time. Think about the relationship between these 3 measures of center and skewedness. Take a look at these 3 data sets, the Ashley, Brandon, and salary data set. Ask yourself for each of them, do you think there are any outliers? I think pretty clearly there's one in the salaries, maybe 2. possibly one in the Brandon data, probably not any in the Ashley. But ask yourself that question. And then ask yourself, how do the three measures of center we looked at line up for the Ashley data, for the Brandon data, for the salary data? And see if you can intuit a relationship maybe between the measures of center and skewedness. In other words, if the data tends to be skewed one direction or have outliers in one direction, does that say something about certain measures of center, how they're going to relate to one another? And if so, if you notice such a relationship, try to look at the math, look at what's underlying the computation for each of those measures of center, and ask, can you explain why that relationship works with the mathematical structure that underlies? So that's where we'll leave off today. Uh, give that a think over the weekend. And when we come back, we'll wrap up section 3.1 and move on to 3.2. Let me stop the recording.